Good morning everyone. Myself R. Ashish. Today we are going to discuss about our digital signal processing experiment number 1. Now going to the first question. Choose a filter to smooth out high frequency noise present in the signal. In this case, we are going to use a filter named moving average filter, which is a finite impulse response filter, which is commonly used to smoothen an array of signal data signal. Generally, it takes L samples of the input time at time and takes average of those L samples and produce a single output point. And it is a very simple low pass filter, and as the L increases we can say that the signal gets more smoother, but this filter has some constraints. This frequent filter is good for a time domain analysis, but whether it comes to the frequency domain analysis, it is not at all a good point. I am going to discuss it right below. Then going back to the formula, it is given that of length, the moving average filter of length L is given the 1 by L sigma k is equals to 0 to L minus 1 x of n minus k. Here I have mentioned the block diagram where x of n is the input and c0, c1, cn minus 1 are the factors, and this delayed version gets multiplied to the factor and just adding them gives the output, the moving average filter, which is a low pass filter generally used to smoothen the frequencies, high frequency noise signal. And here, right, coming back to this, assume that this one is our input signal x of n. When this one was given to a black box which process the 3-point moving average filter, the output would be like this. If it was, we increase the L still more further, for example 51, the output would be like this. And have a look at this transaction, it just remains same, a bit slight in this one, but if we increase it more further 101, the noise has been almost decreased, and we have increased it furthermore. Example for L is equals to 501. It can be said as sort of clear signal without high frequency noise and the smooth signal. But when comes to this, the transaction has been changed. Here look at the input. The input was a high frequency noise, but while come to the after the moving average filter of length 501 output, this transaction has been bent slightly. So this is a good filter to apply the time domain analysis, but not the frequency domain. Now going back to the code and flow, just loading the values of the data and declaring the moving average variable, setup begin, serial begin. This allows the communication data flow from Arduino to the computer at a speed of 9600 bits per second. Obviously we can change the values, some fixed terms, fixed numerical values are there. Now going to the void loop for int I is equals to 0, I less than 100. We are going to take 1000 samples, that's it, and we are going to have a filtered length of 8. The moving average, yeah, j is equals to 8. The formula was quite same from here, so I'm not going to explain this keenly. So here is the output. This is the blue one is the raw data signal, and the red one is the moved average filtered signal. The output of the moving average of length equals to 8. Okay, fine. Now going back to the question paper, the second question, choose a filter to emphasize high slow portions in the signal. Yeah, here we are going to use derivative filters. Generally these derivative filters are of two types. first order derivative filter and 3 central difference derivative filter, 3-point central difference filter, and the formula was quite simple. Y of n is equals to y x of n minus x of n minus 1, which is given right here, and the 3-point central difference filter derivative formula is also given here. Y of n is equals to x of n minus x of n minus 2. There is no argument in this. Now the question comes here. We can apply this filter to emphasize the slopes in two different ways. One way, we can directly apply to the raw data which we have taken at the starting, here the x of x, and we can also apply this filter to the signal which we have been previously obtained, means the signal after we have passed through the moving average filter of length 8. Okay, here I have done both. And this and one more thing, the first order filter and 3-point central derivative filter doesn't give much differ output, but a sort of similar output, but obviously the 3-point central derivative filter is more better than first order one. Here I have applied to the filter data. This is the blue one is the raw data, red one is moving average, and I have applied the first order derivative filter to this, and this is the output. See, we can see the slope points. Okay, now going to the B. If we apply this derivative filter to the raw data, and I have done it right here, this is the raw data, and the green one was the first order derivative filter, and the third one was orange one was the 3-point central derivative filter, red one was the moving average filter. That's no need of this, but I have done for information. See, you can see first order filter and the third order 3-point derivative filter is almost same, but a slight variations. Okay, I prefer, rather than applying it to the raw data, it would be better to use the derivative filter after the moving average filter, so that we can get a clear cut signal. Okay, good. Next, going back to the question number 3, design a moving average filter of length L given. Here we are using n is equals to 1000, so of length L is equals to 800 to extract the baseline shift. Yeah, while we are extracting a signal from a sensor or an electrode or something, there is a lot of things we are getting added to the signals. Those are called as noises, which we doesn't want. And generally for our constraints, the signal which we have obtained, it's said to have 3 components: original PPG signal, baseline wonder noise, and the high frequency noise. Now you know what does the high frequency noise and the PPG signal. Now coming to this baseline drift component, it generally occurs due to the movement of the electrodes or the regular body movements or regular heartbeat irregularities, and some sort of these things may cause to damage to the signal which we are taking. In order to view the baseline drift component from the signal, we can use the moving average filter, but of a high length. Here we have used L is equals to 800, the same, nothing difference, the same as the moving average filter, the same I have done. And the blue one was the raw data signal, and the red was baseline wonder. Okay, next, getting back to the final question, we are at the end. Finding the output of the signal processor which performs the derivative filter and then perform moving average Okay, as I have previously mentioned, the data our data consists of original PPG signal, high frequency noise, and baseline wonder. Yeah. Now here, and this is the blue colored one is the raw data, well known, and the green one was, yeah, right, baseline wonder. I have removed the baseline wonder from the original signal so that I will be obtaining the original PPG signal of combination PP signal and high frequency noise. When these are applied to a moving average filter followed to previously followed to differential filter, we will get the correct signal, means the original PPG signal which was obtained here, the red one. Here you can see this, the red one, the original PPG signal that is obtained after performing derivative filter for for forwarded to moving average filter, and also by removing the baseline wonders. And here is the code as I have explained previously. This is the moving average filter based on the above formula. That's it. Okay, thank you. We're done for today.